two stars. And if you look at it through a telescope, one is bright blue and one is bright yellow. It's really cool to look at. So stars have different colors, and the reason for that is because they have different temperatures. Blue stars, contrary to kind of what you'd expect, are very hot. And this kind of explains that, is when you get a really hot star, the distribution of its energy is more towards blue light. When you start cooling things off, it goes towards red light. And if you let it get even cooler, its peak of the energy it's going to give off isn't even visible. It's in infrared. Or if you get it really cool down here, you can get things that emit in the radio part of the spectrum. Of course, if you go the other way and make something really hot, it can give off mostly ultraviolet light. So what we want to do is figure out how much the sun versus McCargo is going to give off in this range out here, the ultraviolet. This is the equation that kind of controls how these curves look. So what we can do is integrate that for that ultraviolet wavelength. And specifically, it's ultraviolet B wavelength. There's also ultraviolet A wavelengths, which aren't cool. So we want to integrate between this range. I'm going to spare you the calculus this time. Yeah, you're welcome. Doing this, you get that McCargo is going to give off 6.44 times 10 to the 23rd watts per meter squared per steradian. Yeah, weird radians. How many, or units? How many people have heard of steradians? No one. A steradian is kind of like a volume down a tunnel, except instead of being straight, it's in spherical coordinates, so it like expands as you go out. Don't worry too much about it. We'll play with it in a little bit. But watts is the amount of energy in a given amount of time. Meters squared is going to be how big of a target are you. If you're something really big, then you're going to have a lot of target area to absorb that energy, and the steradian is going to have to do with how far away you are. Well, now let's look at the sun. The sun actually gives off a pretty respectable amount. 2.15 times 10 to the 22, same units. Looking at the kind of scientific notation on there, that's only a factor of like 10 less just to start. So, I mean, 10 times as much radiation, roughly. That doesn't sound too bad, does it? Let's take into effect some other things. Other things that are going to be important. McCargo is really close. We're saying it's 10 meters. The sun is really far away, 93 million miles. So that means it's going to spread out all that radiation to make it less potent for the sun, even though it's already less potent. But McCargo is tiny. He doesn't have a lot of surface area to give off all this radiation. Meanwhile, the sun is freaking huge. So it's going to give off a lot more, but be much further away. So how's that going to affect things? Well, if we put in all the units and everything, we get the McCargo is going to hit you with 3.22 times 10 to the 21st watts of ultraviolet. Meanwhile, the sun gives off 2.94 times 10 to the 15th, nearly 1,000,000 times less. But that's not it. Because we also have something called an atmosphere, which has ozone in it, which blocks, thank gosh, most of the UV light. So we only get about 2% of the light in the ultraviolet from the sun. So we need to kind of take out that much from what the sun's doing. And when we actually get the ratio of how much UV you get from McCargo versus the sun, you get 360 or 36.5 million times more UV from McCargo than you do from the sun. Which means if you burn in 10 minutes, being pasty white boy like me, you would burn in a nanosecond, getting within 10 meters of this Pokemon. Crispy Ash. Staying on the Pokemon theme, I think this is like the most requested thing I ever. Let me answer your question first.
Well, have you ever considered, first, the Codex definition says, the heat is inside the shell, correct?
Yes, but you can't keep something locked up. It always leaks out. It will transfer that heat to the shell, and then it's going to hit you once it leaks out of the shell. Yeah. Yeah, so the idea is that you can't ever have something that's a perfect insulator that will prevent the heat from getting out. Eventually, the temperature inside is going to transfer to the shell, and then the shell will equalize at the exact same temperature. You can't do anything about it. So, yeah, McCargo is not something I'd want to catch. But let's talk about other things we want to catch. I think this is the most requested thing I've ever gotten. How does a Pokeball work? I don't know. How does the warp nacelles on the Enterprise work? There's people who've tried to explain that too. So here's my attempt at explaining a Pokeball. I couldn't get a video of this, but there's a couple things that you have to notice about it. First, a Pokeball hits something, it turns all glowy, and then it turns into this kind of beamy thing and goes inside the Pokeball. All right, let's work with it. Two things that we notice about this. First off, the Pokemon doesn't have a cohesive form. It's not still a Pokemon, it's this beamy, glowy thing. Yeah. So it's not like it just shrinks and it's still the same thing. It's weird. The second thing is it can't have mass. Brock doesn't capture a 500-pound Onix and then have a 500-pound Pokeball sitting on his waist. So we could take apart the Pokemon, just break him apart into atoms, which would mean that he's not a Pokemon shape anymore, but he'd still weigh the same thanks to conservation of mass. As somebody said, the way to get around this, let's convert him to energy. This satisfies both things. Cool. But unfortunately, Einstein has something to say about that. Let's start off with a Pikachu, because everybody loves Pikachu. A Pikachu has 5.9 kilograms of mass, according to the Pokedex. A radius of a Pokeball changes, but it's about 2 inches on average. So 0.05 meters, because I'm a scientist, I work in meters and not inches. And the volume of a Pokeball, using that diameter and the volume of a sphere, is that you have 5.2 times 10 to the negative 4th meters cubed. Going back to what Einstein said, who knows this M equals mc squared thing? Yeah, mass and energy, you can change between forms, so we're going to take Pikachu's mass, multiply it by the speed of light squared, and find out how much energy Pikachu is worth. Turns out it's 1.77 times 10 to the 9th joules. Again, we're lacking context, let's work on that. So let's start off. How much air is in that Pokeball? In an average cubic meter of air, there's 3.4 times 10 to the 25th molecules, but we only want that little volume. So inside the Pokeball, there's only going to be 1.8 times 10 to the 22 molecules, and we have that much energy. If we divide it and spread it out amongst all the molecules evenly, and then put that amount of energy that the average molecule has into the Boltzmann equation, we can figure out what the temperature of that air is going to be. Turns out it's going to be 4.8 billion degrees Kelvin, which means, let's go back to Fahrenheit for you guys, 8.6 billion degrees Fahrenheit. That's kind of a hot number. That's cool. Context? Well, let's take temperature, some things we know about. Temperature of a blowtorch, paltry, nice, cool. 2.3 times 10 to the third, so 2,000 degrees Kelvin. Surface of the sun, we talked about that from the cargo, 5.7 times 10 to the third, cool. How about an atomic bomb? 3 times 10 to the fifth, keep going. Core of the sun, 10 to the 7th, keep going. Temperature necessary to fuse oxygen, 10 to the 9th. Temperature of a supernova, 10 to the 11th. Notice I left the hole, guess where Pikachu goes? Whoa! Now, let's look at this again. What's this line say right here? Fuse oxygen? And what is 20% of our atmosphere? Oxygen. Catch a Pikachu, destroy the world. Yeah.
Well, inside that Pokeball, there has to be a computer to do all of this. So how much memory would it take to...
Energy does not equal data. They try to say that sometimes, but it makes no sense.
Well, it just seems to me that the Pokeball would be like a condensed version of a transport meter.
Which doesn't work either. It has the exact same problem, except a person weighs a lot more than a Pikachu. Go over here first.
All that assumes the Pokeball would survive the impact. How would they build it to
What impact?
all the energy from the
The
Pokemon?
energy, no, it doesn't survive. It melts. Yeah.
Is there not like any sort of insulator?
No, it was the same question he was asking. Can you contain that much energy? No. I mean, what's the best insulator we can think of? Well, let's think about the shuttles on the space shuttle, or the tiles on the space shuttle. Those only get up to a few thousand degrees, and then they would melt. We're not talking about billions of degrees for those. And even then, they can only take it for so long. They delay it long enough for the shuttle to land, but keep going, everything will destroy. Plasma? This is a plasma. A plasma is not an insulator. Plasma is really good at conducting heat because you have free electrons which can move around to take the heat wherever it wants to go. The sun is a plasma, yeah. Yes. Why have we established that? Should I go back to my third slide? All right, so what else do we got? Well, this is one of the ones that kind of peeves me off the most. Being a science major, and I hated this in high school, but how many of you took a physics class and they always made you write your units on everything? Isn't that just the most annoying thing ever? It's like I plug it into the equation, it comes out in this, duh. Well, there's actually a good reason to worry about it. Don't just worry about it at the end, worry about it on every step and you can check it as you go. And here's an example of that. So let's say you're traveling at 30 kilometers an hour and you travel for 30 minutes. Well, how far would you go? Using the easy physics equation that I hope everyone knows, distance is the velocity times time, so let's plug stuff in and chug. Plug and chug, 30 kilometers an hour, 30 minutes, 900 kilometer minutes per hour, what? Hells no, you've done something wrong. So what we need to do is we need to get it so everything's in the same units so it cancels out right. We don't want some things in minutes, some things in hours. Let's put it all in the same units and we got 30 minutes is a half an hour, so plug that in. 30 times half is 15 kilometers per hour per hour. The hours over hours cancels out. Anything numerator, denominator, gone. So you get an answer of 15 kilometers. Good answer. I haven't tried this personally, but I've heard that if you just look at your units and take the ACT, SAT, you can do really well on it without knowing any science. Just paying attention to what do I have to do to make the units cancel out correctly. This doesn't always work because as I had in that equation in the last one with Pikachu, there's sometimes these random 3 halves and stuff in there, but at least it gets you a good start. So why is that important? Well, it turns out that there's one anime that I will never forgive for not doing this.
What does the scouter say about his power level? It's 9,000! There's no way that can be...
It's not what 9,000, it's 9,000 what? So I needed to figure out what, because you can't leave me hanging like this. So I wanted to Google this. I just started putting in units of energy. First I tried it with ergs. Ergs are insignificant. If he had 9,000 ergs, he couldn't lift a paper clip. So what about like a normal unit, like a watt? Well, let's put into Google, what does 9,000 watts buy you? It can power one small house for 6 hours a day. I found a couple other things. They were all really boring, but my favorite one was this. If you can't tell what that is, this is something they use at carnivals to make funnel cakes. How many funnel cakes do you think Goku can make an hour?
Over a million?
Over a million?
Over 9,000?
180 funnel cakes. That is all Goku is worth. Oopsie. Alright. So here's my last topic I want to talk about today. I saved this for last because this is the most fun. How many people seen Avatar: Last Airbender? Not the movie, the good series.
Yes. Oh yeah. The movie sucks.
About halfway, I almost walked out of the movie. It made me cry when they summarized a whole relationship with, and they quickly became best friends.
Oh.
Anyway, halfway through the series, roughly, they're all at this kind of airbender village where it was been abandoned because the Fire Nation had destroyed it. And there's some guys living there, and one of them takes Sokka down into these caverns.
Sokka.
Sokka. What is this? Sokka.
Don't mess up the names. Don't get
All right, well, they take him down in this chamber, and he notices that the lamp isn't using fire, it's using lightning bugs. And he's like, what's up with that? And he says, well, we can't take light or fire down here because this whole chamber down here is filled with natural gas that will explode if I do that. He says, I tried that one time and almost burned off my eyebrows. Almost kind of did. So later they're fighting the Fire Nation for control of this thing, and then they go, hey, natural gas, we're out of other weapons, so let's drop a furnace into this cavern where all that natural gas is and we'll blow everything up. Not like we're not sitting on it, but we'll blow everything up, because that's what's important. So they did. They blow everything up. So I want to do a little bit of a demonstration with blowing stuff up. Alright, I gotta unpack this stuff here. It's like triple packed because it's really reactive. Yay! Alright, so in my bottle over here, I just got plain water, and what I got in this bag here is a little can of calcium carbide. Anyone ever heard of that?
Yeah.
What does it do?
It reacts.
Ooh, good job.